Hello guys, you're welcome to my YouTube channel Mathematics Made Easy. So in today's video we'll be solving this beautiful integral from 0 to 1, then the complete elliptic integral first order. So I want to prove that this is equal to 2g, so where g is a Catalan constant. Okay guys, so before we start, don't forget to subscribe to my channel, like my video, share and comment. So thank you guys for watching. All right, so let's start solving this problem. It is a very interesting question. Very interesting question. All right, guys. So let me quickly remind us the integral representation of the complete elliptic integral of the first order. I mean of the first kind. So we know that k of k. So this is equal to integral from 0 to pi over 2, then of 1 over square root of 1 minus k squared sine square theta, then the theta. Okay. So then writing k of k using this word integral, then we are going to have a double integral. So writing that, we are going to have integral from 0 to 1, integral from 0 to pi over 2. Then instead of writing k of k, that is why we are having integral from 0 to pi over 2 of 1 over square root of 1 minus k squared sine square theta. So we're going to have 1 over square root of 1 minus k squared sine square theta. Then we have the k, the theta. Since this is a double integral, we have the k before, then later on we have the k. Okay, so what we are going to do next is to make a substitution. So by making the substitution, we can say it that let sine theta. So if we say let sine theta be equal to u, then you differentiate with respect to u. So if you differentiate sine theta, we are going to have cos theta, the theta. So then if we differentiate u, we're going to have the u. Then you make the theta the subject of the formula. So the theta is equal to the u over, now if we write cos theta in terms of u, so this is what we're going to have. We're going to have square root of 1 minus u squared. Then we have the theta is equal to the u over square root of 1 minus u squared. Okay guys, so let's move on. So this our integral becomes integral from 0 to 1, then integral from 0 to 1 also. Because if we substitute pi over 2 to be theta here, you're going to have 1, because sine pi over 2 will give us 1. Then if we substitute 0 to be theta, sine 0 is 0. Okay, so that's why we're having 0 to 1 also here. All right guys, so let's move on. So we're going to have integral from 0 to 1, integral from 0 to 1, then of 1 over square root of 1 minus k squared u squared, then multiply by 1 over 1 minus u squared. Sorry, square root of 1 minus u squared, the k, the u. Sine theta is now u, that's why we're having u squared here. Okay guys, so I can integrate this thing into, like, I can split it into two parts. So by saying I want to split this into parts, I can firstly integrate this one having k. Okay, so I can firstly integrate it, that is, I can say dealing with. So to make the work so easy for us, so let's do it that way. Dealing with integral from 0 to 1, then of the k over square root of 1 minus k squared u squared. So in this case, u will be constant. So are we together? So in this case, u will be constant, then k will be the variable we are integrating with respect to. Okay, we are integrating with respect to k here. So u will be the constant. So we can also make a substitution here. So by making the substitution, we can say let ku be equal to x. So if ku is equal to x, then we have u decay. If you differentiate this with respect to k, you have u decay is equal to dx. Then you can make decay the subject of the formula. Then we have decay is equal to dx over u. So that's what we're going to have there. So we're going to have 1 over u, then integral from 0 to u. If you make the substitution of the limit, so when k is 1, so we're going to have u is just substitute k to be 1, then we have u. Then when k is 0, just substitute k to be 0, then we have 0. Then we're going to have 1 over u integral from 0 to u, then of the x, then over square root of 1 minus x squared. The integral of the x over square root of 1 minus x squared is the arc sine of x. So what we are going to have now will be 1 over u, then of arc sine of x arc sine of x, then we apply the limit from 0 to u. Then we're gonna have arc sine of u over u. Then if you also substitute 0, arc sine of 0 is 0, so that's what we're gonna have. So then if you integral from 0 to 1 of the k over square root of 1 minus k squared u squared, we're gonna have arc sine of u over u. So that's what we're gonna have. Okay, now since we've integrated this function right here, so what we have now, it is a subfunction with only one variable, which is u. That is, we've simplified this into what? Into one to single integral. Okay, guys, so let's move on to the next page. So moving on to the next page, so we are going to have just a single integral now. Then we have so let me partition my board into two. So then we have integral from 0 to 1, then of arc sine of u, then over u multiplied by the square root of 1 minus u squared du. So this is a beautiful integral that we have now. So we have integral from 0 to 1 of arc sine of u over u square root of 1 minus u squared du. You know, we can also make a substitution here. If you make the substitution, we can say that or we can say let arc sine of u, or we say let arc sine of u be equal to x. Then if arc sine of u is equal to x, you know, u will be equal to sine x. Then if we differentiate arc sine of u, we are going to have 1 over square root of 1 minus u squared du. Then if we differentiate x here, we're going to have dx. So then, you know, if you write this integral right here, we can write it as integral from 0 to 1 of arc sine of u, then over u multiplied by 1 over square root of 1 minus u squared du. So that shows that 1 over square root of 1 minus u squared du is now dx. Then also the limit is going to change. Will it change? Yeah, arc sine of 1, that is pi over 2. You know, if you substitute 1 to be u, so arc sine of 1 is pi over 2. Then if you substitute u to be 0, so arc sine of 0 is just 0. Okay, so we're gonna have integral from 0 to pi over 2. So we know that arc sine of u is now x, then over u, which is sine x. We have x over sine x dx. And since 1 over square root of 1 minus u squared du is now dx, that is why we have dx right here. Wow, this is another beautiful integral. So the next thing I'm going to do here is to apply the Weierstrass substitution. Okay, applying the Weierstrass substitution. So by applying the Weierstrass substitution, I can let t be equal to tan x over 2. So if I say t is equal to tan x over 2, then if we make x the subject of the formula here, so we're going to have x is equal to 2 multiplied by arc tan of t. Okay, that's what we're going to have. Then if we differentiate, we have the x is equal to 2 over 1 plus t squared dt. You know, if you differentiate arc tan of t, we are going to have 1 over t squared dt. So all right, so if t is equal to tan x over 2, then sine x will be 2t over 1 plus t squared. Okay, so sine x is equal to 2t over 1 plus t squared. So that is what we are going to have there. Okay, so let's move on. Now, you know, the limit is going to change since we are making a substitution here. So when x is pi over 2, we are going to have pi over 4. So tan pi over 4 will give us 1. Then when x is 0, we are going to have tan 0, and tan 0 is also what? 0. So therefore, we are going to have integral from 0 to 1. Then x is 2 arc tan of t. So we have 2 multiplied by arc tan of t. Then over, you know, sine x is now 2t over 1 plus t squared. 2t over 1 plus t squared. Then the x is now 2 over 1 plus t squared dt. So we have 2 over 1 plus t squared dt. So we can leave something here. 1 over t squared, I mean 1 plus t squared, we cancel out 1 plus t squared, and then also 2, we cancel out 2. So what we have now is 2 multiplied by integral from 0 to 1, then of arctan of t over t dt. Wow, this is also a beautiful integral. So we have integral of 2, we have 2 multiplied by integral from 0 to 1 of arctan of t over t. Okay, so let's move on to the next page. So this is what we have. We have 2 multiplied by integral from 0 to 1 of the arctan of t over t dt. Let me partition this board also here. Okay, guys, so let me quickly remind us something here. This integral right here is the inverse tangent integral. The inverse will define the inverse tangent integral as follows. The inverse tangent integral is defined on the interval zero less than z less than 1. So we have pi of 2z equals integral from 0 to z, then of arctan of t over t dt. So which is also equal to summation from k is from 0 to infinity, then of minus 1 raised to the power of k multiplied by z raised to the power of 2k plus 1, then everything over 2k plus 1 raised to the power of 2. Now that is beautiful. Now if you now look at this integral right here, the value of z is 1. So then we are going to have the inverse tangent integral then of 1. So this will be equal to, just substitute z here also to be 1. So we substitute z to be 1. So we are going to have integral k is from 0 to infinity, then of minus 1 raised to the power of k. So if you substitute 1 here, is just 1. Then over 2k plus 1 raised to the power of 2. So this is also better, or the Dirichlet beta function. The Dirichlet beta function, beta of s equals summation of k from 0 to infinity of minus 1 raised to the power of k, then of 2k plus 1 raised to the power of s. So we can also say that this summation here is beta of the Dirichlet beta function, which is equal to the Catalan constant. Okay, so this is equal to the Catalan constant. So therefore, we know that pi of 1 is now equal to what? The Catalan constant. Then our integral, we are having 2 here. 2 is multiplying the integral. So we have 2 multiplied by pi of 1. So this will be equal to 2 multiplied by the Catalan constant. Then we have our answer. Hence, the integral from 0 to 1 of the complete elliptic integral of the first kind, the k is equal to 2 multiplied by the Catalan constant. All right, guys, so if you like this kind of video, please don't forget to like my videos, don't forget to subscribe to my channel, share my videos, and comment. Thanks for watching. So see you next time.